Hello there and welcome to the Bedtime Science Stories. I am truly happy you've joined me. Perhaps your day has been long, or maybe you simply enjoy drifting into sleep while contemplating stars, galaxies, and the silent enigmas of the cosmos. Whatever your reason, tonight's voyage is designed just for you. There is nothing you need to do right now. Simply allow your body to settle, your mind to grow quiet, and your thoughts to wander freely, because tonight we will be journeying through the cosmos in its entirety. We will not focus on a single galaxy or star, but on the immense, expanding whole. We will move gently from one concept to the next, learning about black holes, ancient light, dark matter, and faraway galaxies. Some of these ideas may startle you. Others might linger in your mind like a quiet reflection at the edge of slumber. And if these calm explorations help you to find rest, please feel free to like and subscribe. Doing so helps others discover this peaceful space as well. Now, if you are ready, let us begin our journey. The universe could potentially be older than our current estimates suggest. Most prevailing calculations place the age of the cosmos at approximately 13.8 billion years. This figure is derived from measurements of the cosmic microwave background and the observed rate of the universe's expansion. However, not all measurement techniques are in perfect agreement. Certain observations of very ancient stars and galaxies indicate they might be older than this estimate would permit. Other studies question the assumed rate of cosmic expansion, or propose that dark energy's influence may be changing over time. These discrepancies have not yet been resolved, and the majority of astronomers still accept the 13.8 billion year figure. Yet the questions persist. Could the universe indeed be older? Is it possible we have overlooked something fundamental? It is conceivable that what we perceive as the beginning was merely one chapter in a much longer and more mysterious story. There are countless rogue planets drifting through the emptiness of space without orbiting any star. Not every planet is bound to a sun. Some are completely free, floating in solitude through the galaxy with no star to provide warmth or illuminate their skies. These rogue planets may have formed in typical solar systems, only to be ejected by gravitational chaos. Others might have formed independently, like failed stars. They are dark, frigid, and nearly impossible to detect, unless they happen to pass in front of a distant star or emit a faint glow in infrared light. Astronomers estimate there could be billions of such worlds within the Milky Way, perhaps even outnumbering the stars. Each one is a silent world adrift in the darkness, spinning alone in the vast expanses between stars. There are no sunrises, no sunsets, only an endless night punctuated by the faint light of distant suns. The universe might be engaged in an endless cycle of rebirth. The standard cosmological model describes a universe that began with a Big Bang and will continue expanding, possibly forever. Yet some theories imagine a different narrative, one where the universe undergoes repeated cycles of expansion and contraction. In these models, the universe does not end in a cold fade or a final collapse. Instead, it resets itself. After reaching a certain point, it might rebound, collapsing inward before exploding outward into a new phase of expansion. Each cycle could erase the old structures, while preserving subtle traces of what existed before. These ideas remain speculative, but they are deeply intriguing. They suggest the universe may have no true beginning or end, only a rhythm playing out across spans of time too vast to comprehend. One universe giving birth to another, over and over again. The most ancient light we can observe dates from about 380,000 years after the Big Bang. Before that moment, the universe was a dense, glowing fog, so hot and thick that light could not travel far without being scattered. But as it expanded and cooled, it reached a critical turning point. Atoms formed, the fog dissipated, and light was suddenly free to stream across space. That primordial light is the cosmic microwave background, and we can still detect it today. It is the most ancient direct signal from the universe, originating not from stars or galaxies, but from the cosmos itself as it was becoming transparent. The photons we detect now have been journeying for more than 13 billion years, stretched by the expansion of space into long, cool microwaves. This light is faint but ever-present, a quiet glow that carries the memory of the universe's earliest moments of clarity. Some stars are orbited by planets composed almost entirely of diamond. In certain solar systems, the chemical environment is very different from our own. If a planet forms with an abundance of carbon relative to oxygen, and the internal pressures are sufficiently high, a remarkable transformation can occur, resulting in a diamond planet. Astronomers have identified at least one such candidate, a dense world orbiting a pulsar, likely the remnant of a dead star. Based on its mass, density, and composition, the entire planet may be a crystalline form of carbon. In essence, a giant diamond. It is far too hot to sparkle, and would not appear jewel-like up close. Yet deep beneath its surface, immense carbon crystal structures could extend for thousands of kilometers. These strange worlds are not common, but they remind us of the incredible diversity found in the universe. A planet might be made of rock, another of gas, and sometimes, a planet made of crystal. The universe may have no edge, only an endless curvature. It is tempting to imagine the cosmos as having a boundary, a border we could eventually reach if we traveled far enough. But space does not appear to function in this way. According to the principles of general relativity, the shape of space is determined by its contents. Current evidence suggests that the universe is either infinite, or so immensely vast and curved that it loops back upon itself. If this is true, you could, in theory, travel in a perfectly straight line forever and eventually return to your starting point, not by encountering a wall, but by wrapping around the curved fabric of space. This is similar to how traveling across the Earth does not reveal an edge, only a globe. The universe may operate on the same principle, but on a far grander scale. Not infinite in a static sense, but infinite in the potential for journey. Our sun may once have had a twin, and that sibling could still be out there somewhere. Some astronomers theorize that our sun was born with a companion star, formed from the same cloud of gas and dust over 4 billion years ago. Many stars are born in pairs, and there is little reason to believe our sun was an exception. If it existed, this lost sibling would have drifted away long ago, pulled apart by the slow, gravitational tides of the Milky Way. It might still be out there, orbiting the galaxy on a different path, invisible to us now. Some theories have even linked this hypothetical twin, nicknamed Nemesis, to mysterious patterns of extinction on Earth, though there is no solid evidence for this connection. Still, the idea endures that our sun, so steady and solitary in our sky, may once have shared its birth with a silent partner, long since vanished among the stars. A single raindrop of material from a neutron star would weigh more than Mount Everest. Neutron stars are the collapsed cores of massive stars, incredibly dense remnants left behind after supernova explosions. They are only about 20 kilometers in diameter, yet their mass exceeds that of our sun. The matter within them is so densely packed that a single teaspoon would weigh billions of tons. If you could imagine a raindrop composed of neutron star material, it would be heavier than any mountain on Earth. This level of density defies all our everyday experience. Atoms are crushed together so tightly that electrons and protons merge into neutrons, forming a kind of superfluid neutron soup. Neutron stars are extreme objects, small, dark, immensely heavy, and often spinning rapidly. In their quiet, immense mass, they hold the memory of stellar collapse, a final state where matter becomes nearly pure gravity. Light from a single galaxy can sometimes reach us from multiple directions. Light does not always travel in a straight line. In regions of space where gravity is exceptionally powerful, such as near massive clusters of galaxies, the fabric of spacetime itself is curved. This curvature bends the path of light, much like a lens of glass bends a beam. This phenomenon is called gravitational lensing. One of its most peculiar effects is that we can sometimes see several distinct images of the same distant galaxy, arriving from different angles. These images can appear as arcs, smudges, or even complete rings. They are not duplicates in space, but duplicates in our perception, the result of light taking different paths through warped spacetime to reach us. In a few rare instances, astronomers have witnessed the same supernova explosion appear multiple times, as its light arrived via different gravitational routes. It is a quiet reminder that in the universe, even light can become lost, take a longer path, and still eventually find its way to us. The first stars may have burned 1,000,000 times more brightly than our sun. The very earliest stars were unlike any we observe today, born from the pure hydrogen and helium that remained after the Big Bang. These stars, known as population 3 stars, likely formed with no heavier elements at all, causing them to be tremendously massive, hot, and short-lived. Some may have been hundreds of times more massive than the Sun. They would have consumed their nuclear fuel rapidly, shining with a brilliance 1,000,000 times that of our own star, before collapsing in spectacular explosions after only a few million years. None of these primordial stars survive today, but their brief existence fundamentally changed the universe. They forged the first heavy elements, seeded galaxies with light, and set the stage for everything that followed, including us. Their light has long since faded, but their fingerprints remain, etched into the chemistry of ancient gas clouds and the quiet structure of the early cosmos. Dark matter streams through your body even as you sleep. As you lie still, dark matter flows silently around and through you. It is not an invisible mist, but a form of matter that does not interact with light. It neither reflects, emits, nor absorbs it. However, it does possess mass and responds to gravity. Our galaxy is enveloped by a vast halo of dark matter. As the Earth moves through this halo, trillions of dark matter particles are thought to pass through every square centimeter of your body each second. They do not collide with your atoms. They leave no trace, yet they are there, ghost-like, ever-present, and essential. Without dark matter, galaxies would not hold together, cosmic structures would not have formed, and the universe would be profoundly different. We still do not know what dark matter is composed of, but we know this much: it is part of your world, passing through you silently and continuously, even as you sleep. Some galaxies glow faintly despite containing very few stars. In the quiet depths of the universe, astronomers have discovered galaxies that shine, yet possess scarcely any stars. These ghostly systems are rich with gas and dark matter, but show little to no evidence of ongoing star formation. Some may have had their stars stripped away during violent gravitational encounters with other galaxies. Others may never have formed many stars to begin with. A few are nearly invisible except when viewed in specific wavelengths of light, appearing as faint smudges in deep sky surveys. These galaxies challenge our understanding of how galaxies form and evolve. If they are abundant in dark matter, why have they not given birth to stars? If they once contained stars, where did they go? These dim, quiet systems drift through space like forgotten relics of cosmic history, reminding us that not every galaxy is filled with blazing light. Some simply exist, unseen and enigmatic. The universe possesses a cold spot that, according to our models, should not exist. Within the cosmic microwave background, the faint afterglow of the Big Bang, there is a region of sky that is unusually cold. It is not merely slightly cooler than its surroundings, it is significantly colder. and far larger than scientists anticipated. This cold spot spans hundreds of millions of light years, and its presence does not perfectly match the smooth, random fluctuations we would expect from the physics of the early universe. Some theorize it could be the imprint of an immense cosmic void. Others wonder if it might hint at something even stranger, such as a collision between our universe and another during the initial moments of cosmic inflation. No current explanation provides a perfect fit. The cold spot remains one of the most quietly puzzling anomalies in cosmology. It is not a glaring inconsistency, but a subtle whisper that something in our universe may not be exactly as it seems. The moon is slowly moving away from us. Each year, the moon drifts a small distance farther from Earth, approximately 3.5 centimeters. This is roughly the same rate at which your fingernails grow. This gradual retreat has been occurring since the moon formed around 4.5 billion years ago. At that time, it was much closer, and a day on Earth was only a few hours long. The cause is tidal friction. As the moon's gravity pulls on Earth's oceans and the planet rotates beneath them, a small transfer of energy gradually pushes the moon into a wider orbit. It is a quiet, relentless process, imperceptible on human timescales, yet unmistakable over eons. In the far future, Earth and the moon may become tidally locked, forever showing the same face to one another. For now, it continues to slip away, little by little, as we spin beneath its distant, glowing light. Binary stars can exchange their outer layers like dancers in close embrace. In some binary star systems, the two stars orbit so closely that their outer atmospheres begin to touch. As they evolve, one star may swell and transfer matter onto its companion, creating a delicate, spiraling exchange of material. Sometimes this transfer is calm and steady. At other times, it triggers bursts of light, rapid rotation, or even a complete merger of the two stars. The underlying physics is complex, but the image is oddly graceful. Two stars locked in a tight orbit, spinning close enough to brush against and blend with one another. One star may end up stripped down to its glowing core, while the other becomes swollen and enriched. Their fates are inextricably linked. Some of the most unusual objects in the universe, such as certain types of supernovae or tightly bound neutron star pairs, originate from these intimate binary systems. It is a reminder that in space, even stars can share, change, and sometimes merge. The vacuum of space is not truly empty. Even in the deepest, darkest reaches of space, far from any star or galaxy, the universe is never completely void. According to quantum physics, what we call a vacuum is actually a sea of fleeting activity. Tiny particle-antiparticle pairs flicker into existence and vanish almost immediately. These quantum fluctuations occur constantly and everywhere, creating a kind of restless background to reality itself. They can influence the motion of particles, affect the behavior of fields, and even contribute to the energy of empty space. This is part of what gives rise to dark energy, the mysterious force driving the accelerated expansion of the universe. So, when we picture the depths of space as silent and still, that image is only partially accurate. Beneath the quiet lies a dance of probabilities, a hidden hum of creation and annihilation, always present just below the surface of nothingness. Time may flow at different rates in different parts of the cosmos. We often think of time as a steady, universal rhythm, ticking at the same pace for everyone, everywhere. But in reality, time is deeply intertwined with gravity, motion, and the shape of space-time itself. In regions where gravity is intense, such as near a black hole or a dense galaxy cluster, time slows down relative to places with weaker gravity. This is not merely theoretical, it has been confirmed by experiments, satellites, and atomic clocks. Some cosmologists speculate whether time could also vary on even grander scales. Could different regions of the universe experience time at slightly different rates, due to the way the cosmos expanded in its earliest moments? The idea is speculative, but it opens strange and fascinating possibilities. In a cosmos governed by relativity, even time may not be absolute. It can stretch, slow, or bend, quietly shaped by the space through which it flows. The Milky Way is surrounded by a hidden halo much larger than the visible galaxy. When we look at images of our galaxy, we see a luminous spiral of stars, dust, and gas arranged in beautiful arms. But enveloping this familiar structure is something vast and mostly invisible, the galactic halo. This is a huge, spherical cloud of diffuse gas and dark matter that extends far beyond the visible edge of the galaxy, reaching out to distances many times greater than the span of the disk itself. This halo contains ancient star clusters, stray stars, and immense amounts of unseen mass. It is held together by gravity, shaped by a history of collisions and mergers, and plays a crucial, quiet role in the galaxy's overall stability. Though we cannot see it directly, we infer its presence from the motion of stars and the bending of light. The Milky Way, it turns out, is merely the bright heart of something much larger, a glowing center wrapped in invisible, embracing arms. We have detected light from a galaxy that existed just 200 million years after the Big Bang. The universe is approximately 13.8 billion years old. But light does not travel instantaneously, it moves through an expanding cosmos, stretched and diluted along its journey. This is why we see galaxies not as they are now, but as they were in the distant past. Recently, astronomers using the James Webb Space Telescope identified light from a galaxy that existed a mere 200 million years after the Big Bang, a blink of an eye on the cosmic scale. That light has been traveling toward us for over 13.5 billion years. The galaxy itself is small, faint, and primitive, yet it holds vital clues to how the first structures in the universe formed. Observing it is like peering through a narrow window into a world we were never meant to witness. The universe in its earliest chapters, when darkness was just beginning to give way to the first stars. The large-scale structure of the universe resembles a neural network. When astronomers map the positions of galaxies across immense distances, a surprising pattern emerges. Galaxies are not scattered randomly. Instead, they cluster along thread-like filaments with vast, empty regions known as cosmic voids in between. This interconnected web stretches for billions of light years and is often called the cosmic web. What is striking is that when viewed from a sufficient distance, this structure looks uncannily similar to a neural network in the human brain. Dense nodes of galaxies act like neurons, and the filaments resemble axons connecting them. Of course, this resemblance is purely structural. The universe is not a conscious entity. Yet it is quietly beautiful to consider that the largest known structure, and the one within your own mind, though shaped by entirely different physical laws, can appear so strangely alike. Stars can sing, even through the vacuum of space. There is no air in space to carry sound as we know it, but stars still produce deep, resonant vibrations that travel through their interior gases like seismic waves through a planet. These pressure waves cause the star to pulse and oscillate, and scientists can detect them by observing minute changes in the star's brightness or surface motion. The field that studies this is called astroseismology, literally, the seismology of stars. Each star has its own unique set of internal frequencies, like a fingerprint, determined by its size, structure, and age. By listening to these stellar vibrations, scientists can peer into the hearts of stars and learn what is happening beneath their surfaces. It is a form of cosmic echolocation, a way to hear the music of stars across light years, even if the song itself is silent to human ears. Some stars are older than the galaxies they currently reside in. Galaxies are not built all at once. They form over vast stretches of time, merging with smaller systems and drawing in stars and gas from their surroundings. This means that some of the stars within a galaxy can be older than the galaxy's present structure. They may have formed in earlier, smaller galaxies that later merged to form the larger one we see today. These ancient stars are often found in the outskirts of galaxies, or within globular clusters, tightly bound groups of stars that orbit far from the galactic core. Some of these stars are over 13 billion years old, nearly as old as the universe itself. They carry the chemical signature of a much younger cosmos, when there were far fewer heavy elements and only the simplest atoms existed. These stars are like cosmic fossils, quiet survivors from an era before the galaxy had fully assembled. Their light is ancient. Their stories began long before much of what we know had even taken shape. There exist galaxies that appear to have no dark matter, and we do not fully understand why. Dark matter is thought to be the invisible scaffolding that holds galaxies together. It explains why stars in the outer regions of galaxies orbit faster than expected, and why galaxies cluster in the patterns they do. However, in recent years, astronomers have found a handful of galaxies that seem to defy this rule. These galaxies behave as if they contain little to no dark matter at all. Their stars move as if only the visible matter is present. This discovery was entirely unexpected and does not fit neatly into current models. Some scientists suggest the dark matter was stripped away during past galactic collisions. Others wonder if we still do not fully comprehend the true nature of dark matter. Whatever the explanation, these anomalous galaxies serve as a reminder that the universe still holds profound secrets, and that the principles we believe to be universal may not apply in every case. The sun resonates like a giant, booming bell. Deep within the sun, sound waves ripple through the searing plasma, bouncing from one layer to another and setting the entire star into subtle, continuous vibration. These waves are not like sounds we can hear. They are pressure waves, low, slow, and far below the range of human hearing. Yet, with sensitive instruments, scientists can detect them and use them to study the sun's internal structure. This field of study is called helioseismology. By observing how the sun resonates, scientists can map what is happening deep beneath its surface, its density, rotation, and even hidden flows of hot gas. In this sense, the sun acts like a vast musical instrument, complex and always playing its deep, resonant tones. We simply require the right tools to listen, and what we hear helps us understand not only our own sun, but the nature of stars throughout the universe. Galaxies tend to align along filaments made of something we cannot see. The largest structures in the universe are not composed of stars or gas, but are shaped by something invisible, dark matter. Over billions of years, this dark matter formed enormous filaments that stretch across the cosmos. Galaxies form and move along these filaments like beads on a string. We cannot see the filaments directly, but we can infer their presence by observing how galaxies cluster and how light bends as it passes through these regions. These filaments can span hundreds of millions of light years, connecting vast clusters of galaxies. Between them lie great voids, merely empty regions where very little matter exists. The dark matter filaments act as a hidden framework for the visible universe, dictating how galaxies grow and where they migrate. And yet, we still do not know what dark matter is. The structure is there, immense, unseen, and quietly holding the cosmos together. Space itself can stretch faster than the speed of light. Under normal circumstances, nothing can move through space faster than light. However, space itself is not bound by this rule. During the initial moments after the Big Bang, space expanded so rapidly that different regions were pulled apart, faster than light could travel between them. This was not motion through space, but the expansion of space itself. Even today, distant galaxies are not rushing away from us because They are moving quickly through space. They are receding because the space between us and them is stretching. If they are sufficiently far away, this stretching causes them to recede faster than light, which is why we will never see them again. This does not violate the laws of physics, but is a quiet consequence of how space behaves on the grandest cosmic scales. The universe does not need to hurry, it simply expands, calmly and relentlessly, beyond our ability to follow. Our solar system moves through space in a helical spiral. It is easy to picture the planets orbiting the Sun in neat, flat circles. But if we zoom out to a larger perspective, a more complex motion emerges. The Sun itself is moving, orbiting the center of the Milky Way at nearly 1,000,000 kilometers per hour. As it travels, the planets are pulled along in its wake, not merely circling the Sun, but spiraling through space behind it. This combined motion creates a helical pattern, akin to a corkscrew or a twisting ribbon. Everything is in motion: the planets, the Sun, the stars, and the galaxy itself. There is no true stillness in space, only a graceful, ceaseless drift. Even as we sleep, we are tracing slow, vast spirals through a galaxy in motion, wrapped within layers of orbits, within orbits, a dance so immense we never feel it. Even the void of space has a temperature. If you were to travel far from all stars, planets and galaxies, into the deep intergalactic void, you would find yourself surrounded by what seems like pure emptiness. Yet, even this vacuum possesses a temperature. It is approximately 2.7 degrees above absolute zero, a remnant of the cosmic microwave background. This is the leftover glow from the Big Bang, now stretched and cooled by billions of years of cosmic expansion. This faint radiation permeates the entire universe. No matter where you go, it is there. It is the quiet thermal signature of the universe's infancy, still lingering, still measurable. In the distant future, it will cool even further. In trillions of years, the universe may approach absolute zero, but will likely never quite reach it, because even in the vastest emptiness, a faint echo of its primordial heat remains. Quantum fluctuations may have shaped the entire cosmos. At the very smallest scales of reality, far smaller than atoms, the universe behaves in an inherently unpredictable manner. Tiny, random fluctuations in energy can appear and vanish in an instant, a consequence of the uncertainty principle in quantum physics. According to many cosmologists, these fleeting, random blips were magnified during the universe's first moments by a process called inflation. As space expanded at an unimaginable rate, these tiny fluctuations were stretched to cosmic proportions. They became the seeds for all future structure, the regions where matter would begin to clump, where galaxies would eventually form, and where stars would ignite. In other words, the grand cosmic web of galaxies, filaments, and voids may all trace their origin back to fleeting, random events at the smallest possible scale. Everything we observe today may have been born from the subtle trembling of nothingness. Dying stars can pulse with a rhythm like a heartbeat across millions of years. Not all stars end their lives in a sudden, violent explosion. Some fade away more gradually, and during their final stages, they can pulsate, swelling and shrinking in regular cycles. These stars, known as variable stars, change in brightness over time. In some cases, these changes are steady and predictable, repeating like a slow, cosmic heartbeat. The pulsations are caused by changes in the star's outer layers as gases expand and cool, then collapse and heat up again. Some stars complete a pulse every few days, while others take months or even years. These rhythmic stars have been invaluable to astronomers for measuring vast distances in space, since their pulsation patterns are directly related to their intrinsic brightness. They also serve as quiet reminders that even in death, stars can keep time, not with a clock, but with a long, slow breath. Our solar system resides inside a giant bubble of hot gas. If you could perceive light in invisible wavelengths beyond what the human eye can detect, you would discover that our solar system is situated within a vast, glowing bubble of hot gas. This is known as the local bubble, and it extends for hundreds of light years in every direction. This bubble is thought to have been carved out by ancient supernova explosion stars that died long ago, blasting shock waves that heated and cleared out the surrounding gas. Now, our solar system drifts quietly through this region of low density, surrounded by a shell of hotter gas and dust. It is not a danger to us, nor something we can feel, but it is there, a kind of quiet chamber around us, born from stellar violence in the distant past, now forming a gentle part of our galactic neighborhood. There is a vast, empty region lying behind the Great Attractor. The Great Attractor is a mysterious gravitational anomaly, a region of space so massive that entire galaxy clusters, including our own Milky Way, are slowly drifting toward it. But behind this immense concentration of matter lies something even stranger, a region known as the dipole repeller, where space appears unusually empty. This is not merely an area with fewer galaxies, it is a vast cosmic void, stretching across hundreds of millions of light years. Strangely, its emptiness seems to exert a repulsive effect, pushing galaxies away. Together, the Great Attractor and the dipole repeller create a quiet gravitational tug-of-war that helps to shape the motion of our local universe. We are drawn forward by unseen mass and pushed from behind by an immense emptiness. It is a reminder that in the cosmos, both presence and absence can dictate the paths we follow. Neutrinos pass silently through the Earth and through your body. At this very moment, trillions of particles called neutrinos are streaming through your body, and you will never feel them. Neutrinos are incredibly lightweight, neutral particles produced in enormous quantities by the Sun, exploding stars, and even the early universe itself. They interact so weakly with normal matter that they can fly straight through an entire planet, or through your body, without leaving a trace. A tiny fraction are detected by sensitive instruments buried deep underground, where rare collisions allow us to study them, but the vast majority pass through completely unnoticed. These particles are everywhere, all the time, silently streaming through space and matter alike. They travel at nearly the speed of light, and yet they almost never touch anything. The universe is filled with this unseen motion, even when everything feels perfectly still. The most massive stars can collapse directly into black holes without a supernova explosion. We often imagine the death of a massive star as a cataclysmic supernova, a brilliant explosion that lights up the galaxy. But for the very most massive stars, the end can be strangely silent. Some stars are so immensely heavy that when they exhaust their nuclear fuel, their cores collapse inward under gravity so completely and suddenly that even the outer layers fall straight in. There is no explosion, no brilliant farewell, just a sudden disappearance. This process is known as direct collapse. In a fleeting moment, a star is gone, replaced by a black hole, silent, invisible, and crushingly dense. Astronomers have even observed stars that seem to vanish without a trace, as if their light simply blinked out. It is a reminder that not all cosmic endings are fireworks. Some are merely whispers into the dark. Galaxies can orbit one another like moons around a planet. We often think of galaxies as isolated islands in space, but many exist in small groups where they interact and even orbit one another. Our own Milky Way, for example, has dozens of smaller satellite galaxies. The Large and Small Magellanic Clouds are the most famous of these. These companion galaxies move around the Milky Way much like moons orbit a planet, tracing long, elliptical paths through space over billions of years. Sometimes, larger galaxies gravitationally strip stars from their smaller companions, forming long streams and tidal tails that stretch for millions of light years. Over immense timescales, a smaller galaxy may be completely absorbed and merged with the larger one. These cosmic dances unfold with a slow, stately grace on a scale we can scarcely imagine. In the quiet of deep space, even galaxies can keep each other company. The universe's brightest explosions may come from collapsing magnetic stars. There is a rare type of stellar explosion known as a magneto-hyperflare, and it may be one of the most luminous phenomena the universe can produce. A magneto is a neutron star with an unimaginably powerful magnetic field, trillions of times stronger than Earth's. If a massive star collapses to form a magneto, and then releases its stored magnetic energy in a sudden, catastrophic event, it can produce a burst of light and energy far more powerful than a typical supernova. These events are thought to be responsible for some long-duration gamma-ray bursts, flashes of high-energy radiation that travel across the universe, and can briefly outshine entire galaxies. The explosion itself may last only seconds, but its light can reach us from billions of light years away. It is one of the universe's most intense phenomena, created by a small, dense object wrapped in magnetic fire, collapsing in on itself. The edge of the observable universe is not the edge of the universe itself. When we look out into space, there is a fundamental limit to how far we can see, approximately 46 billion light years in every direction. This marks the boundary of the observable universe. It is not a physical wall or a barrier, it is simply the greatest distance from which light has had time to reach us since the Big Bang, given the ongoing expansion of space. Beyond this horizon, the universe almost certainly continues. We just cannot see it yet, because its light has not had time to travel to us. Furthermore, because the expansion of space is accelerating, some regions of the universe are now moving away from us faster than light. This means their light will never reach us, not even if we wait for an infinite amount of time. The observable universe is thus like a bubble of visibility, not the full extent of reality, but merely the portion accessible to us. Beyond it lie more galaxies, more stars, perhaps continuing forever. Some galaxies eject jets of plasma that extend for millions of light years. At the heart of many galaxies lies a supermassive black hole. Sometimes, as matter spirals toward this black hole, not all of it is swallowed. Some becomes caught in powerful magnetic fields and is blasted outward in narrow, incredibly energetic jets. These jets, composed of plasma moving at nearly the speed of light, can stretch far beyond the confines of their host galaxy, reaching lengths of millions of light years. We detect them glowing in radio wavelengths, forming enormous lobes that mark their incredible extent. Galaxies with such features are called radio galaxies, and their jets rank among the largest structures in the universe. It is a strange irony that some of the most powerful outflows in the cosmos originate from the regions around black holes, from which not even light can escape. It seems that even silence can, in its own way, leave a profound mark. There is a star that orbits the Milky Way in the opposite direction to most others. The vast majority of stars in our galaxy orbit in the same general direction, following the galaxy's rotation. But there are exceptions. At least one known star, catalogued as HVCO 475439, moves in a retrograde orbit, going against the flow like a salmon swimming upstream. How did it acquire this unusual path? One possibility is that it was originally part of a smaller galaxy that merged with the Milky Way long ago, and its orbit is a relic of that different galactic system. Alternatively, it may have been flung into this backward path by a gravitational slingshot encounter, perhaps involving a black hole or a dense star cluster. Whatever its history, this star is a quiet reminder that not all celestial bodies follow the common rules. Even within the vast, orderly clockwork of the galaxy, there are wanderers that travel their own unique paths. The center of our galaxy smells like raspberries and rum. This may sound whimsical, but it is based on a scientific discovery. Astronomers studying the chemical composition of a dust cloud near the Milky Way center identified a molecule called ethyl formate. On Earth, this compound is associated with the flavor of raspberries and the scent of rum. Of course, the galactic center does not actually have a scent in the way we experience the vacuum of space, cannot carry odors like air does. However, the presence of these molecules hints at the complex organic chemistry taking place in deep space. Interstellar clouds contain alcohols, sugars, and even precursors to amino acids. This is not life itself, but it is the kind of chemistry that life requires. So, while space itself may not smell of fruit or liquor, it is filled with the silent, floating building blocks of these very scents, drifting between the stars. One galaxy is on a collision course with the Milky Way, and the process has already begun. The Andromeda Galaxy is our closest large galactic neighbor, and it is steadily moving toward the Milky Way. Currently, it is about 2.5 million light-years away, but that distance is slowly closing. In approximately 4 billion years, the two galaxies will begin to merge. Interestingly, the outermost halos of both galaxies, their vast, diffuse clouds of hot gas and dark matter, are already starting to overlap. So, in a sense, they have already begun to touch. The eventual merger will be more of a slow, graceful blending than a violent crash. Stars are so widely spaced that they will mostly pass by one another without colliding. Over time, the two spiral galaxies will coalesce into a single, larger elliptical galaxy, sometimes referred to as Milkomeda. This cosmic union is a long-term event, already set in motion, a meeting playing out over billions of years. The cosmic microwave background still glows all around you. Every part of the universe, including the space you occupy right now, is permeated by a faint glow known as the cosmic microwave background. This is the afterglow of the Big Bang, light released when the universe was about 380,000 years old. At that time, the cosmos was a hot, dense plasma. When it cooled sufficiently for atoms to form, light was finally free to travel across space. That light has been streaming through the universe ever since, stretched into microwaves by the relentless expansion of space. Today, we detect it as a nearly uniform glow coming from all directions. It is not something you can see or feel, but sensitive instruments can pick it up as a kind of cosmic whisper. This glow is the oldest light we can possibly observe, a quiet signal from the universe's infancy, still echoing through space and time. Some supernovae are powered by an invisible collapse, not by light. Supernovae are renowned for their brilliant cataclysmic explosions that can briefly outshine entire galaxies. However, not all supernovae are luminous. Some are what astronomers term failed supernovae. In these cases, the core of a massive star collapses to form a black hole, but the outer layers do not explode outward in a visible flash. Instead, they may fall inward, silently feeding the newborn black hole. On rare occasions, we have watched stars that appeared stable suddenly vanish from view. There was no explosion, no fading glow, just darkness. These disappearances suggest a collapse so total that almost all the energy is swallowed by the black hole. Tremendous violence occurs, but most of it remains hidden from our view. It is a reminder that not all stellar deaths are announced with light and sound. Some occur in profound silence. Deep within the cosmic web, there are entire galaxies composed mostly of gas and dark matter. We often picture galaxies as bright spirals or glowing ellipticals, teeming with billions of stars. But some galaxies are barely visible at all. These faint systems contain very few stars, yet they still possess significant mass, primarily in the form of gas and dark matter. They are extremely difficult to detect with conventional telescopes, and often appear only as faint smudges or through indirect measurements. Some of these galaxies may be failed system structures that never managed to form many stars, perhaps because they were stripped of their gas or heated too early in cosmic history. Others might represent a temporary phase in galactic evolution. What they all share is their subtlety. They produce no brilliant fireworks, no sweeping spiral arms. They possess only a quiet gravitational presence. They remind us that not all galaxies shine. Some simply exist. Black holes can collide and merge in a cosmic dance. When two black holes orbit one another, they emit ripples in the fabric of spacetime known as gravitational waves. As they lose energy through these waves, they gradually spiral inward, eventually merging in a final, dramatic instant. Two invisible giants become one. These collisions do not produce light, but they send powerful bursts of gravitational waves radiating across the universe. The first direct detection of such an event occurred in 2015, confirming a prediction made by Albert Einstein a century earlier. Since then, we have detected dozens more of these cosmic mergers. Each one tells the story of massive objects colliding in distant galaxies long ago. These black hole mergers happen quietly and invisibly, yet with incredible force, converting entire solar masses worth of energy into waves that ripple through the very fabric of the cosmos. For a brief moment, spacetime itself sings. Some stars die in slow motion, taking billions of years to fade away. Not every star ends its life in a sudden, violent explosion. Smaller stars, like our Sun, expire much more gradually. After they exhaust their hydrogen fuel, they expand into red giants, eventually shedding their outer layers into space. What remains is a dense, hot ember known as a white dwarf. This stellar remnant no longer generates energy through nuclear fusion. It simply radiates its residual heat into space, very, very slowly. A white dwarf can take billions of years to cool, gradually dimming until it becomes a cold, black dwarf. However, the universe is not yet old enough for any black dwarfs to have formed. Every white dwarf that has ever existed is still glowing, quietly fading in the dark. The death of these stars is less like a firework and more like an ember, cooling gently over cosmic time. Time flows more slowly near a black hole compared to Earth. In Einstein's theory of general relativity, gravity does not merely pull on matter, it warps the fabric of space and time. The stronger the gravitational field, the more slowly time passes relative to regions of weaker gravity. Near a black hole, where gravity is extreme, this effect becomes profound. If you were to orbit just outside a black hole's event horizon, time for you would pass much more slowly than for someone far away. Minutes near the black hole could equate to years elsewhere. This is not science fiction, it is a real, measured phenomenon known as gravitational time dilation. We have even observed it in a milder form with satellites in Earth's orbit. Around black holes, however, it becomes a dominant feature. In a way, black holes do not only trap light, they also stretch and distort time itself. The void between galaxies is colder than any environment we can create on Earth, far from the warmth of stars, planets, or even dense gas clouds. The vast expanses between galaxies are astonishingly cold. The temperature there plummets to just a few degrees above absolute zero, about 2.7 Kelvin. This is colder than any natural location on Earth and colder than most laboratory environments we can produce. This profound chill arises from the near-total absence of particles and energy. There is simply nothing present to retain or generate heat, only a sparse scattering of stray atoms and the faint, uniform glow of the cosmic microwave background. These intergalactic voids are the quietest, most lonely places we know of, enormous and empty, stretching for millions of light years. They are the universe's deepest shadows, holding only the background whisper of creation. The universe is becoming more transparent as it ages. In the early universe, light could not travel freely. The cosmos was filled with a hot, opaque plasma fog of free electrons and atomic nuclei that constantly scattered photons. But as the universe expanded and cooled, it reached a point where electrons combined with nuclei to form neutral atoms. Suddenly, light could move through space virtually unhindered. This event, known as recombination, occurred about 380,000 years after the Big Bang and released the cosmic microwave background radiation we detect today. Since that time, the universe has continued to grow more transparent. The formation of galaxies and stars created new sources of light, and as matter has spread out, there is less and less to obstruct a photon's path. With time, the darkness has become clearer. Space, once glowing and opaque, now allows light to pass through almost unimpeded. We have captured the shadow of a black hole. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. The black hole itself cannot be seen, but the bright ring of hot gas swirling around it reveals its silhouette. This particular black hole resides at the center of the galaxy Messier 87, located about 53 million light-years away. The image shows a dark circular shadow, the region from which no light can escape, encircled by a brilliant halo of radiation bent by intense gravity. Capturing this image required years of global coordination, linking telescopes across the planet to act as a single, Earth-sized instrument. The result was more than just a picture, it was a quiet triumph of science, providing our first direct glimpse of one of the universe's most enigmatic objects, not through speculation or theory, but through the actual detection of light. You can see a galaxy with your naked eye from your own backyard. Most galaxies are so incredibly distant that even powerful telescopes reveal them only as faint smudges. But there is one galaxy you can see without any optical aid at all, the Andromeda Galaxy. On a clear, dark night in the northern hemisphere, it appears as a soft, hazy patch of light in the sky, just visible to the unaided eye. It is over 2.5 million light-years away, meaning the light you see began its journey long before modern humans existed. Andromeda contains about 1 trillion stars, more than twice the number in our Milky Way, and it is slowly moving toward us. It is a profound thought, but you can simply look up and see an entire galaxy with no telescope, no filter, just the night sky, your own eyes, and the soft glow of something vast and ancient, drifting in the dark. A tiny satellite detected the whisper of a distant black hole collision. In 2015, the LIGO Observatory detected something extraordinary, a faint ripple in spacetime originating from more than 1 billion light-years away. It was caused by the collision of two black holes, which sent gravitational waves propagating across the cosmos. These waves are incredibly subtle. By the time they reach Earth, they stretch and squeeze space by less than the width of a single proton. Yet, with exquisitely sensitive instruments, we can now detect them. LIGO and other gravitational wave observatories act like cosmic ears, listening to the deepest rumblings of the universe. This first detection confirmed a prediction Einstein made a century ago, that even in the silence of space, the most massive events can send out waves. We can now sense the faint chirp from the merger of invisible giants, captured by a delicate detector on a small, quiet planet. Some regions of the universe are expanding away from us forever. The universe is not only expanding, this expansion is accelerating. As space stretches faster and faster, some galaxies are being carried away so rapidly that their light will never be able to reach us, even if we waited for all eternity. The space between us and those galaxies would grow at a rate that light could never overcome. They have already passed a point of no return, slipping beyond our cosmic event horizon. Eventually, more and more of the universe will fade from our view, not because it ceases to exist, but because its light can no longer bridge the ever-widening gap. This is not something we will notice in our daily lives, but over billions of years. It means the visible universe will gradually shrink. The cosmos is not just growing, it is also quietly letting go of parts of itself. Some black holes may be primordial, formed before the first stars. Most black holes are created by the collapse of massive stars. However, there is another possibility: black holes that formed in the universe's earliest moments, before any stars had ignited. These are known as primordial black holes. They may have been born from tiny, intense fluctuations in the dense, hot conditions that existed just after the Big Bang regions where gravity pulled matter together into ultra-dense knots. Some of these primordial black holes could be incredibly small, while others might have grown over time. We have not yet directly confirmed their existence, but if they are real, they could help explain the nature of dark matter, seed the formation of the first galaxies, or provide new insights into the universe's infancy. They would be older than stars, older than galaxies, silent fossils from the first seconds after time began. Entangled particles may link distant corners of the cosmos. Quantum entanglement is one of the most perplexing phenomena in physics. When two particles become entangled, their properties remain connected no matter how far apart they are separated. A change in one particle will instantly affect the other, even across vast cosmic distances. This does not allow for information to be transmitted faster than light, but it does suggest that at a fundamental level, reality is deeply interconnected. Some physicists speculate that entanglement could play a role in the very fabric of spacetime, perhaps even helping to bind space together. In theory, particles that became entangled in the early universe could still be linked today, their connection stretched across the expanding cosmos. If this is true, there may be invisible quantum threads connecting vastly separated regions, quiet echoes from the dawn of time, still present in the emptiness between galaxies. The vacuum of space exerts a quantum pressure. Even in a perfect vacuum, where no atoms, particles, or radiation exist, there is still energy. Quantum physics tells us that empty space is not truly empty. Instead, it is filled with fleeting, restless fluctuations, virtual particles and antiparticles blinking in and out of existence. Fields shifting minutely, always in motion. This activity creates a background pressure known as vacuum energy. On the largest scales, this pressure may be responsible for dark energy, the force driving the universe's accelerating expansion. Unlike other forms of energy, vacuum energy does not dilute as space grows, it remains constant. The more space there is, the more vacuum energy exists, causing the expansion to accelerate further. It is a strange concept that the more nothingness you have, the more potent its influence becomes. The quiet, persistent pressure of empty space may be the very force that is driving the cosmos apart. Black holes radiate a faint heat over trillions of years. Black holes are famously dark, so dense that nothing, not even light, can escape their gravitational pull. However, thanks to the work of physicist Stephen Hawking, we know they are not completely black. According to quantum theory, black holes can emit a very faint glow, now known as Hawking radiation. This occurs at the very boundary of the event horizon, where virtual particle-antiparticle pairs can pop into existence. Occasionally, one particle falls into the black hole while the other escapes, becoming a real particle. This process represents a tiny loss of energy from the black hole. Over incredibly long time scales, trillions upon trillions of years. For a black hole the mass of the Sun, this slow leakage can cause the black hole to shrink and eventually evaporate completely. It is the quietest form of demise imaginable, not an explosion, but a long, slow fade into nothingness. The universe contains more plasma than solid matter. When we think of matter, we typically imagine solids, liquids, and gases. But the most common state of matter in the universe is something else entirely: plasma. Plasma is an ionized gas, a seething cloud of particles where electrons and atomic nuclei move independently. It is found in stars, in the solar wind, in interstellar space, and in the vast regions between galaxies. In fact, most of the visible matter in the cosmos exists in this state. Plasma behaves differently from other forms of matter. It conducts electricity, responds strongly to magnetic fields, and can flow like a fluid across immense distances. On Earth, we encounter it in lightning flames or neon signs. But in space, plasma is everywhere, glowing, flowing, and shaping much of what we observe, even when we are unaware of it. This fourth state of matter is the dominant substance of the visible universe. Gravitational waves travel at the speed of light. Gravity does not only exert a pull, it can also create ripples. When massive objects like black holes or neutron stars collide, they send waves through the fabric of spacetime itself. These gravitational waves stretch and compress space as they propagate, moving outward in all directions, and they travel at the speed of light, the ultimate speed limit of the universe. It took decades to develop instruments sensitive enough to detect these incredibly faint signals. But now we can listen to these cosmic ripples from Earth. Each wave carries encoded information about the distant cataclysm that produced it, the masses involved, the spin of the objects, and the nature of the spacetime warping. Gravitational waves are silent to our ears, but they are real, measurable, and represent the gentlest of shudders in the deep structure of the cosmos. The cosmic web connects galaxies across the universe. If you could map the positions of all galaxies on the largest possible scale, you would see a beautiful, intricate pattern, a vast interconnected network of filaments and voids known as the cosmic web. Galaxies are not distributed randomly, they cluster along invisible threads of dark matter and gas, stretching like tendrils between immense clusters. Where these filaments intersect, we find superclusters, enormous knots of galaxies. Between them lie vast, quiet voids, regions nearly devoid of matter. We cannot see the entire cosmic web at once with a telescope, but its structure emerges from large-scale surveys of the sky. It resembles a neural network, a foam, of the branching patterns of a tree. It is the architecture of the universe on its grandest scale, not random, but woven together, as if grown rather than built. The James Webb Space Telescope can see galaxies that may no longer exist. The James Webb Space Telescope was designed to peer farther into space, and thus further back in time, than any telescope before it. Because light takes time to travel, the most distant galaxies appear to us as they were billions of years ago. Some of the galaxies that Webb observes may have long since ceased to exist in the form we see them. They may have merged with other galaxies, faded away, or transformed entirely. But their light is still in transit, a snapshot frozen in time, crossing the vastness of space long after the source itself has changed. This is one of the quiet peculiarities of astronomy. Telescopes do not show us the universe as it is now, but as it was at different moments throughout its history. Every deep field image is also a time machine, a gallery of vanished light. Distant galaxies glow with light that left them before the Earth was formed. When you observe a galaxy that is billions of light years away, you are not just seeing across a vast distance, you are looking back in time. The light from that galaxy began its journey long before the Earth existed, before the Sun formed, before our solar system had even begun to coalesce. Some of the galaxies we see today emitted their light over 10 billion years ago. That glow has traversed an expanding universe, stretched and diluted during its long voyage, until it finally reaches our telescopes. In a sense, we are watching the ancient past of the universe in real time. The stars we see in those distant galaxies may have died eons ago. Their enduring light is a soft reminder that the night sky contains stories older than our world itself. Entire galaxies can be hidden behind clouds of dust. Even something as immense as a galaxy can be obscured by cosmic dust. In some regions of space, thick clouds of interstellar dust composed of tiny grains of carbon and silicates can block the light from objects behind them. When a galaxy lies behind one of these clouds, much of its visible light can be absorbed. We often only discover these hidden galaxies when we observe in wavelengths that can penetrate the dust, such as infrared, radio, or X-ray light. Astronomers have uncovered entire galaxies this way, lurking behind what was once thought to be empty sky. It is a reminder that in space, appearances can be deceiving. Darkness does not always mean nothing is there. Sometimes it merely means an object is waiting to be seen in the right light. Some galaxies are surrounded by perfect circles of lensed light. Occasionally, the gravity of a galaxy bends the light from an object even farther behind it. If the alignment is precise, this bending can create a phenomenon known as an Einstein ring, a perfect, or nearly perfect, circle of distorted light. This is a form of gravitational lensing where the mass of the foreground galaxy curves spacetime, acting as a cosmic lens for the background light. Einstein rings are rare but beautiful, appearing as glowing loops suspended in space. They are formed not by physical structures, but by perspective and gravity. The lensed light can come from a distant galaxy, a quasar, or even a supernova. These rings help astronomers measure the mass of galaxies, map the distribution of dark matter, and study the early universe. They are silent, perfect illusions, natural lenses created by the warped shape of space itself. The universe may be infinite. When we gaze up at the stars, it is natural to wonder if the cosmos has a boundary, an edge to everything. However, current observations suggest that space may extend forever. We can only see a finite portion, the observable universe, but beyond that horizon, the universe may continue without limit. There would be no edge, no center, just more galaxies, more stars, more space. If this is true, it means that the vast majority of the universe will forever remain beyond our reach. No matter how far we look or how long we wait, we will never see all of it. An infinite universe does not necessarily imply infinite possibilities, but it does suggest an endless vastness, a quiet, immeasurable expanse that stretches on gently and without conclusion. Cosmic rays strike the Earth from the depths of space. Every second, high-energy particles known as cosmic rays bombard our planet. Some originate from the Sun, others from distant parts of our galaxy, and some from even beyond. These particles are primarily protons and atomic nuclei, accelerated to incredible speeds by exploding stars, black holes, or other mysterious cosmic engines. Most are deflected by Earth's magnetic field or absorbed by the atmosphere, but a few reach the surface, and an even smaller number pass through your body. These particles are generally harmless in small quantities, but they are a constant reminder that space is not empty. It is alive with motion, energy, and invisible messengers from far-off cataclysms. Every so often, a cosmic ray strikes a scientific detector and tells a story that began light years away. A particle's journey from a supernova to your sky. The phrase "before the Big Bang" may be meaningless. The concept of a time before the Big Bang seems logical, but it may not correspond to physical reality. According to general relativity and many cosmological models, time itself began with the Big Bang. That moment was not merely the birth of matter and energy, but also the beginning of space and time as we understand them. Asking what came before is akin to asking what is north of the North Pole. Some theories propose a preceding state or a multiverse, while others describe a quantum realm where time behaves differently or does not exist. But in most standard models, before the Big Bang is not an epoch we can meaningfully discuss. The Big Bang was not an explosion within space, it was the beginning of space and time. Astronomers once mistook quasars for nearby stars. When quasars were first discovered, they appeared as faint, point-like sources of light, almost indistinguishable from ordinary stars. However, their light spectra were bizarre, and their brightness fluctuated in puzzling ways. It took years for astronomers to realize that these were not stars at all, but incredibly luminous cores of distant galaxies. A quasar is powered by a supermassive black hole at the center of a galaxy, surrounded by a swirling disk of intensely hot, falling gas. This gas heats up and glows with phenomenal brightness, sometimes outshining the rest of the galaxy combined. The first identified quasars were so far away that their light had been traveling for billions of years to reach us, yet they appeared as tiny star-like points. It was a case of mistaken identity that led to one of the most brilliant discoveries in modern astronomy. Our local group of galaxies is falling toward a hidden region. The Milky Way is not stationary, along with the Andromeda Galaxy and dozens of smaller companions. It drifts through space as part of a collection known as the local group, and this entire group is, in turn, moving toward a gravitational anomaly called the Great Attractor. But beyond that lies an even more massive structure, the Shapley supercluster, and perhaps other concentrations of mass still hidden from our view by the dense plane of our own galaxy. These distant, massive regions exert a gravitational pull that we can measure, even though we cannot see them directly. It is as if our entire galactic neighborhood is sliding slowly towards something enormous, wrapped in shadow. We do not yet know all that lies in that direction, only that we are being drawn toward it, pulled by the collective weight of unseen cosmic giants. We are living in the universe's stellar springtime. At this moment, the universe is rich with stars forming, burning, and exploding. But this is a relatively recent development in cosmic history. For the first several hundred million years after the Big Bang, there were no stars at all. The first ones ignited in darkness, lit up their surroundings, and began the long process of cosmic evolution. Since then, the rate of star formation has risen, peaked, and is now slowly declining. We now live in what could be considered a cosmic spring, a time when new stars are still being born, though less frequently than in the past, and far more often than will occur in the distant future. One day, the last stars will form. After that, the universe will gradually darken. But for now, it remains alight with new beginnings, bright enough to inspire wonder, and quiet enough to allow for rest. In the distant future, stars will cease to be born. Star formation relies on the availability of cold, dense clouds of hydrogen and helium gas that can collapse under their own gravity. Over time, this primordial fuel becomes locked away in stars, blown into intergalactic space by supernovae, or heated to temperatures too high for collapse to occur. Billions of years from now, galaxies will exhaust their reserves of star-forming material. The remaining stars will age, burn out, and fade away. First, the massive, blue giants will disappear, followed by sun-like stars. And finally, the long-lived red dwarfs will cool into darkness. The universe will not end suddenly, it will dim by degrees, quietly and gently. What remains will be black holes, white dwarfs, neutron stars, and the profound silence of a cosmos grown cold. It will not be a tragic end, merely a deep and lasting stillness. Most of the matter in the universe is invisible. When we look out at the universe, at the stars, galaxies, and nebulae, we are seeing only a tiny fraction of what is actually there. The majority of the cosmos's matter does not emit, reflect, or absorb light. This invisible substance is called dark matter. Although we have never detected it directly, we know it exists because of its gravitational effects. Galaxies rotate faster than they should if only visible matter were present. Light from distant objects bends more than expected. Galaxy clusters hold together with more gravitational strength than their visible mass can account for. All of this points to the existence of a hidden form of matter, outweighing ordinary matter by a factor of about 5 to 1. Dark matter is everywhere, shaping the large-scale structure of the universe. We simply cannot see it. It is a quiet, invisible framework upon which the visible cosmos is built. Light from the first galaxies has been stretched by cosmic expansion. When light travels through the universe, it does not merely move, it is stretched. This is because the fabric of space itself is expanding. As the universe grows, it pulls the light waves along with it, lengthening their wavelengths. The light that left the earliest galaxies billions of years ago has been stretched from visible light into the infrared part of the spectrum. This process is known as cosmological redshift, and it is one of the primary tools astronomers use to measure cosmic distances and ages. The more stretched the light, the farther away and older the source. With telescopes like James Webb, we can now observe this ancient light, now softened and reddened by its long journey across an expanding universe. What began as the brilliant glow of young, hot stars now arrives as a faint whisper, stretched by the relentless breath of space itself. The universe may be a hologram. This sounds like science fiction, but some physicists have seriously considered the possibility that our three-dimensional universe might be a projection from a two-dimensional surface. This is known as the holographic principle. It arose from studies of black holes, where the information about everything that falls in appears to be encoded on the event horizon surface, rather than within its volume. Some theories suggest the entire universe could operate on a similar principle. What we perceive as three-dimensional space and depth could be a kind of elaborate illusion, arising from information encoded on a distant, two-dimensional boundary. This idea is not proven and is unlikely to affect our daily lives, but it serves as a gentle reminder that reality, even at its most solid and tangible, may not be exactly what it seems. Space may have a granular structure at the smallest scale. To our eyes, space appears smooth and continuous. Even under powerful microscopes, it seems like an empty void. However, some theories of quantum gravity suggest that space itself may be composed of tiny, discrete units like grains or pixels in a vast digital image. This smallest possible scale is known as the Planck length, about 10 to 35 meters. At this level, the smooth, continuous nature of space may break down into a foamy, grainy texture. We do not yet have the technology to probe this scale directly, or even to test the idea conclusively. But if it is true, then everything, stars, galaxies, your thoughts, even your sleep, exists not within a perfect void, but within a universe that has a fundamental, granular structure all the way down. Some stars spin faster than a kitchen blender. Certain stars rotate at astonishing speeds, so fast that their equators bulge outward and their surfaces become a blur. Neutron stars, the incredibly dense remnants of massive stars, are particularly notable for this. A type known as a millisecond pulsar can spin hundreds of times per second. This means a city-sized sphere of nuclear matter rotates faster than the blade of a blender. These objects emit powerful beams of radiation that sweep across space like cosmic lighthouses, ticking with extraordinary precision. Many of them are in close binary systems, where they pull material from a companion star, a process that spins them up to these incredible velocities. They are among the fastest spinning objects known in the universe, and also serve as some of the most accurate natural clocks, ticking silently through the night. The universe could end in a slow, quiet fade. Cosmologists once debated whether the universe would eventually recollapse in a big crunch, but the evidence now strongly suggests a different fate: slow, endless expansion. As galaxies drift farther apart and star formation grinds to a halt, the cosmic background will grow darker. Existing stars will burn out one by one. Black holes will gradually evaporate via Hawking radiation. Even matter itself may eventually decay. The universe will become colder, quieter, and increasingly emptier state known as heat death. This is not a sudden event, but a long, gentle fading away. Over trillions of years, the cosmos will grow still as energy spreads thinly and all structure dissolves. It is an end not with fire or ice, but with silence, a universe that whispered itself into existence, and will eventually whisper itself away. Some galaxies have superwinds that blow away their own stars. At the heart of certain galaxies, particularly those with intense star formation or active supermassive black holes, powerful winds can blast outward from the central regions. These galactic superwinds can carry gas, dust, and even young stars with them, streaming out into intergalactic space for tens of thousands of light years. They are driven by the combined energy of countless supernova explosions and the radiation from the active galactic nucleus. Over time, these winds can strip a galaxy of the gas needed to form new stars, leaving it red and dead. They also play a crucial role in distributing heavy elements forged in stars throughout the cosmic web, seeding future generations of stars and planets. In this way, a galaxy can be said to breathe inhaling matter, igniting stellar life, and then exhaling material back into the void. The far future of the cosmos is an endless dark ocean. Trillions of years from now, the universe will be unrecognizable. Galaxies will have drifted so far apart that each will appear isolated in an abyss of darkness. New star formation will have ceased entirely. The remaining stars will slowly burn out. Even the faint glow of white dwarfs will eventually fade. What remains will be a sparse collection of cold remnants, black holes, neutron stars, and the thin echo of ancient light. Over unimaginable time scales, black holes will evaporate, and matter itself may decay into subatomic particles. Eventually, all that will be left are these particles, drifting through an ever-expanding, nearly perfect vacuum, silent, slow, and utterly alone. This final state is known as the heat death of the universe. But it is not a violent conclusion, it is a vast, dark stillness, a cosmic ocean with no waves, no wind, and no shore. We might be living inside a giant cosmic void. The universe is not uniform, it is filled with clusters and superclusters of galaxies, and between them, enormous regions of near emptiness called voids. These voids can span hundreds of millions of light years and contain very little matter. Some cosmologists have proposed that our Milky Way galaxy may reside within one of these underdense regions, a local void that is less densely packed with galaxies than the cosmic average. If true, this could help explain certain discrepancies in measurements of the universe's expansion rate and patterns in the cosmic microwave background. Living inside a void does not change our everyday experience, but it implies that what we perceive as our local emptiness is part of a much larger structural pattern, the quiet interior of a cosmic bubble, gently drifting within an invisible web of gravitational forces. Magnetars possess magnetic fields trillions of times stronger than Earth's. A magnetar is a specific type of neutron star, a city-sized stellar remnant with a magnetic field of almost unimaginable power. Earth's magnetic field is strong enough to guide a compass needle. A magnetar's field is so intense it could distort the structure of atoms, erase credit cards from thousands of miles away, and tear apart matter. These colossal magnetic fields are transient, decaying over thousands of years, but while they last, they can produce spectacular flares and bursts of high-energy radiation. A single magnetar flare, even from across the galaxy, can be detected by satellites orbiting Earth. No laboratory on Earth could ever generate such magnetic forces. Magnetars are among the most extreme objects in the universe, incredibly dense, silent, and shrouded in invisible, immense power, like stars that have become pure memory and magnetism. The universe's largest known structure is a giant quasar group. In 2013, astronomers identified an immense structure composed of numerous quasars, stretching over 4 billion light-years across. This colossal grouping, known as a large quasar group, is so vast that it challenges the cosmological principle, which states that the universe should appear relatively uniform on the largest scales. This structure exceeds the theoretical maximum size for such formations. It consists of dozens of quasars linked across an enormous volume of space, suggesting that the early universe may have permitted the formation of larger patterns than previously thought possible. Whether it represents a single, coherent structure or a statistical fluke is still a matter of scientific debate. Regardless, its discovery reminds us that the cosmos is more complex and perhaps more interconnected than our models can always predict. Black holes can twist space into a funnel where time slows to a crawl. A black hole does not merely capture light, it profoundly warps the fabric of spacetime. As you approach its event horizon, space becomes increasingly curved, and time dilates. It flows more slowly relative to a distant observer. To someone far away, time near the black hole's edge would appear to almost stop. This warping creates a geometry akin to a funnel, steep, narrow, and one-way. All paths within lead inexorably toward the central singularity. The closer you get, the more the roles of space and time seem to interchange, with the inward direction becoming a direction in time rather than space. There is no return from this descent. This twisting of spacetime is not merely a metaphor, it is the actual geometry, dictated by general relativity, written into the very fabric of reality by the immense force of gravity. Some regions of the universe will never be able to see each other again, because the universe's expansion is accelerating. Some parts of the cosmos are already moving apart from one another faster than the speed of light. This means that even if we wait for an infinite amount of time, the light from those regions will never reach us. The same is true in reverse. We can never send a signal to them. Over time, more and more of the universe will slip beyond our cosmic horizon. Each galaxy or cluster will become an isolated island, surrounded by an ever-growing darkness, forever separated from the rest. This does not violate the laws of physics, as nothing is moving through space faster than light. Instead, space itself is stretching, calmly and unstoppably, separating one part of the cosmos from another for all eternity. The heaviest elements, like gold, are forged in stellar explosions. Gold is rare on Earth not just economically, but cosmically. It cannot be produced in the core of an ordinary, living star. Instead, it is created in the most violent events in the universe, the collisions of neutron stars, or in certain types of supernova explosions. In these extreme environments, atomic nuclei are smashed together under immense pressure and heat, forming heavy elements like gold, platinum, and uranium. These newly forged atoms are then scattered into space, mixed into interstellar gas clouds, and later incorporated into new generations of stars, planets, and, eventually, living beings. Every gold ring, every tiny fleck of gold dust, was born in a cosmic catastrophe, a quiet trace of stellar violence, now resting in the palm of your hand. In this sense, gold is not merely beautiful, it is ancient and stellar, a treasure forged in the fires of the universe. The space between galaxies expands, while light travels through it. When we observe light from a distant galaxy, we are seeing it as it was in the past. But we are also seeing light that has been stretched during its journey. As the universe expands, the distance the light must traverse increases, and the light waves themselves are stretched, their wavelengths growing longer. This is the phenomenon of cosmological redshift. The light is not losing energy by colliding with anything. The space through which it moves is simply expanding. In effect, the universe stretches the light signal on its way to us. When we look at a faraway galaxy, we are therefore witnessing more than just its age and distance. We are seeing a record of how space itself has evolved since the moment That light began its voyage, a silent testament to the universe's steady, relentless expansion. There are sound waves frozen into the structure of the cosmos. In the very early universe, before atoms formed and light could travel freely, matter and radiation were locked together in a hot, dense plasma. Within this plasma, waves of pressure similar to sound waves in air rippled through the medium, creating regions of slightly higher and lower density. These acoustic oscillations left a permanent imprint on the distribution of matter. Today, we can detect this imprint as a preferred scale in the clustering of galaxies, a specific distance that appears more frequently between galaxy pairs than any other. This fossilized echo, known as Borean acoustic oscillations, is subtle but measurable. It is the signature of a cosmic sound wave that rang out from the universe's earliest moments. A wave that never completely faded away, but instead became frozen into the large-scale structure of everything we see. The cosmos is still ringing from its earliest moments. In the first fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion known as inflation. This explosive growth left behind ripples, tiny quantum fluctuations that were stretched to cosmic proportions. These ripples became the seeds for all the structure we see today: galaxies, stars, planets. They also left an echo, which we detect as minute temperature variations in the cosmic microwave background. We may one day also detect the primordial gravitational waves from this epoch, faint, rhythmic pulses in the fabric of spacetime. The universe may seem quiet now, but it still carries the memory of that initial, violent vibration, like a giant bell that is still humming softly, long after it was struck. The universe is vast, and you are a way for it to know itself. Of all the strange and wonderful facts in astronomy, perhaps the most quietly profound is this: you are made of stardust. The carbon in your cells, the calcium in your bones, the iron in your blood, all were forged in the hearts of long-dead stars, scattered across space by stellar explosions, and eventually gathered together to form our planet and life upon it. You are not separate from the cosmos, you are a part of it, momentarily conscious. You are a flicker of awareness in a universe that would otherwise only consist of moving, burning, and cooling matter. In this sense, the universe has grown eyes, and through your eyes, it looks back at itself, wonders at itself, undreams about itself. And even now, as you drift toward sleep, it keeps on dreaming. Thank you for spending this time here, floating through the cosmos with me. We have journeyed across vast distances, past dying stars and newborn galaxies, listening to the ripples in spacetime and echoes from the earliest moments of creation. And somewhere within all of this, in the light of ancient stars, in the silence between galaxies, in the quiet shimmer of cosmic dust, there was you, breathing slowly, your thoughts growing soft, perhaps already asleep. This universe is filled with motion and mystery, but it also contains profound stillness. It holds heat, light, and gravity, but it also holds peace. And the fact that we can come to know it, piece by piece, in calm and in quiet, is something truly beautiful. So, wherever you are now, whether still awake or drifting beyond the edge of thought, may your dreams tonight be gentle. May your body rest as peacefully as starlight on calm water. And may you carry with you, even if only faintly, the memory of a universe that glows not only above you, but within you. If you happen to still be listening, you are welcome to continue to the next chapter now. And if you'd like to drift off to more stories like this one, softly told and filled with wonder, please consider subscribing. There is always more to explore, one sleepy soul at a time. Good night.